In this video, we will go over problem 16.33, where we're asked to calculate the pH at the equivalence point for the titration between HCl at 0.2 molar HCl and 0.20 molar methyl amine. So 0.20 molar HCl is your strong acid. So we want to designate that as a strong acid, whereas 0.20 molar methyl amine is a weak base. So that is something that we get from the textbook. One of the things here is to recognize the definition of equivalence point. The definition of equivalence point is basically where the concentrations are equal. If you do a titration and the amount of titrant, its concentration, equals the amount of titrand, then you have the equivalence point. The concentrations of both species, in this case the strong acid and the weak base, are equal to one another. So the question we have to ask ourselves is, we're given a concentration, we're not given a volume. We're not given a volume. So what is the volume that will neutralize 0.20 molar HCl and 0.20 molar methylamine? The answer is the same volume. So take 5 mils, take 10 mils, whatever amount of mils. 5 mils will neutralize 5 mils, both are 0.2 molar. 10 mils will neutralize 10 mils, both of them are 0.20 molar. Because they're the same concentration, you can actually have the same volumes, and the final concentration after mixing will be 1/2. So the final concentration, you can test this for yourself, whether you use 5 mils or 10 mils or 50 mils, they both neutralize one another. So when you mix them, the final concentration will be half, right? So if you mix 5 mils with 5 mils, both are same concentration. 10 mils with 10 mils, both are same concentration. The total concentration after mixing will be 1/2. So the final concentration after we mix at the equivalence point will be 0.10 molar. So first thing we want to do is write the equation between methylamine and HCl. This is the weak base going with the strong acid. And at the equivalence point, the concentrations of both of these species are going to be 0.10 molar. So our equation here is going to be methylamine, and all of this is happening in water. It's going to react with our strong acid, HCl, and you're going to get the methyl ammonium ion, CH3NH3+. Don't forget the positive formal charge. And as we stated before, the concentrations at the equivalence point, the final concentration is going to be half because they're the same concentration. So it's going to be 0.1 molar. Now, how much of the strong acid? Remember, HCl is a strong acid. That's key to this. It's going to be all of it, right? All of it, because HCl is a strong acid. So a strong acid will work to 100%. There we see the conjugate acid and the conjugate base. So as typical for an equivalence point type of problem, we have no reactants. Well, this is a violation of an equilibrium, right? Every equilibrium must have some reactants left over with some products. So now we're going to have to use the back reaction. So at the equivalence point, we have to always use the back reaction. The reaction going the other way. And this is a hallmark of doing any type of acid-base titration problem at the equivalence point. So we're going to do the back reaction. So the back reaction is CH3NH3+, and this is all in water. And we're going to go and reverse this. Here, the methyl ammonium, the conjugate acid, will do what acids do and give off a proton, giving us hydromonium ion. And as a result, we get CH3NH2. So basically where the reaction is going in the opposite way because the strong acid ate up all the base. So we have to use the back reaction. The Ka for this is going to be here. We're going to have to look it up. This is a standard Ka. Ka has water as a reactant and produces H3O+ as well as the conjugate base. So looking this up, so the book tells us the Kb here is 4.4 times 10 to the minus 4, and we know that Kw over Kb is equal to Ka, so we can do that, or we can look this up in the book to get our value of Ka for that particular acid. So we went about using Kw equals divided by Kb, so Kw is 1.00 times 10 to the minus 14, divided by Kb, which was given to us for methylamine. This is something we got from the book, actually, 4.4 times 10 to the minus 4. And that's going to be a very insignificantly small number of 2.27 times 10 to the minus 11. So let's write that down. So 2.27 times 10 to the minus 11. Now we'll do our ice table, 0.1, 0, and 0. And it's going to be minus x plus x plus x for our ice table, and at equilibrium, the methyl ammonium of the back reaction, because remember, at the equivalence point, all of the acid ate up all of the base. So we're using the back reaction. 0.10 minus x, and this will be plus x, and that will be plus x. So let's do our Ka expression. It's going to be products over reactants. I'm just substituting H plus for hydromonium ion. Once again, these are one and the same. H and Ka, we just calculated it to be 2.27 times 10 to the minus 11. And H plus is going to be X, and as well as CH3NH2, methyl amine will also be X, so that will be X squared divided by 0.10 minus X. So now we can do our low ionization assumption, and obviously, when you're at 2.27 times 10 to the minus 11, that is so small that very little is going to go that way. Very little is going to go to the right. So we can safely assume that 0.1 minus x is about approximately 0.10, because again, 10 to the minus 11 means very little is going to go in the forward direction. But enough of it will have to go, because remember, we're at an equilibrium, and you cannot have all products or all reactants. The fundamental definition of an equilibrium is that you must have reactants and products at the end of the reaction completion. So doing the low ionization assumption, 2.27 times 10 to the minus 11 times 0.10 is 2.27 times 10 to the minus 12. Square rooting that on our calculator, getting 1.51 or so times 10 to the minus 6. Here you want to put the units of molar, and that x is, as we should know by now, the same thing as the x in our ice table, which represents the proton, H3O+. So we'll do our pH by taking the minus log of the just computed x value, and that's going to be minus log of the number of x that we just solved for, 1.51 times 10 to the minus 6. And doing that on our calculator, don't forget to take the negative off because it's minus the log, so it's going to be 5.82. Key to solving this problem is recognizing that at the equivalence point, the concentration will be half, right? Half. Remember, we started off with equal 0.20 molar of methylamine and 0.20 molar of the strong acid.